Okay, and we are going to jump back to where we were earlier today when we were thinking about what we need to do to design a new station. So this is a station design toolbox. It's, well, helps you when you're starting from, I know I want to pick a camera, I know I want to pick a site, and helps you decide a little bit about the choices that you might make when you're designing your station. So like we talked about in the camera selection lecture, the quality of the data depends on good sampling and thinking a lot about the choices you're making as you're building your station. This is designed to simplify the station design process by making it easy to visualize what your station is going to look like. It's meant to have a really low bar for entry, so anybody who's able to open up MATLAB and start up a GUI should be able to do this. And so you really don't need a lot of coastal imaging skill in order to start working on this. You can use it both for a UAV data collection and for a fixed camera. And this will help you decide on what camera to use, or you can kind of create your own camera. And it exports everything to a KML so you can look at it in Google Earth or whatever your favorite Earth browser is to get a sense of what you might look at. And so again, this is supposed to simplify the design process, make it easy for anybody with a GoPro to be able to have a nice station design and can be used by an expert or a new user. The toolbox requires MATLAB 2018 or later. It also requires the CIRN support routines, which are available in our GitHub repository. It requires the Open Earth toolbox, so you can create those KMLs, and Google Earth Pro or whatever you like to look at your KML files in. And you can find it, the Station Design Toolbox, on our repository. So here's what the structure of the toolbox looks like. You can either load in an input file, you can create your own input file after running the GUI one time. You can choose a camera type if you're not really sure, but there are a few stock options in the GUI, or you can input information about a focal length, a camera tilt, heading, an elevation, and the number of cameras you want, and generate your own camera type. Say you have a camera that's not already in the toolbox. Once you input that information, the GUI computes the camera azimuths based on the field of view that you're looking for and the number of cameras that you have. It takes care of some image warping issues. I'll talk about that later. And then eventually plots the results. Like I mentioned, it relies on the support routines toolbox for creating a projection matrix, so the P matrix that we've been talking about all day long, rather than solving for your intrinsics and extrinsics. You're going to actually create a virtual one for this case. It's going to help. The support routines has code to plot the camera footprint out in real world coordinate system and to produce resolution maps, really similar to the ones that we produced with the QSIT toolbox, but now this is for a virtual camera that doesn't yet exist in the world. Again, the Open Earth toolbox we use to generate our KML overlays and convert between different coordinate systems. What you get out of the toolbox are the camera footprints and resolution maps. You can also save the inputs that you used so that you can recreate what you produced in the toolbox in case you want to go back in a week and show somebody else what you did. So to run the toolbox, we're not actually going to do the demo in MATLAB today, but I'm just going to tell you a little bit about it so you can do it. And like I mentioned, it's a GUI where you're just pushing buttons through. Within the toolbox that you download from GitHub, there is a PDF that has a user guide that will walk you through all these steps. And you can start it up just by clicking on the Station Design GUI file, or you can go to the Station Design GUI and press enter. Okay, so once you open up the GUI, you check this box first if you want to use an input file that you already had, or if you didn't have one, you can either choose to manually enter the data here or choose from, or you could choose the camera that we already have and then manually enter information about the elevation of the camera that you expect you're going to use. So for example, if you know you're going to put it on top of a building, you could estimate where that building is, or if you're going to use a mast where you can adjust the height of the mast, you could try different elevations to see what you like best. Put in the latitude, longitude, and EPSG code to help with some of the conversions. And then you can use these buttons to visualize the camera fields of view and save your results. So this is just a list of all of the input information that you would include in an input file and an example of what an input file looks like. So there again, you can start to go, you can do this through the GUI or start to play around with build your own input files if you prefer not to use the GUI. So once you've input all of your camera information, the next step is to plot the camera footprint with that button, and you get something like this. And so here, you've got a local coordinate system centered on your camera, and you can see what the fields of view of each camera would be. And again, here, going back to some of the things we talked about earlier, we know for a particular camera type, we've already pre-calculated the size of that chip, and we know the focal length of the lens that's on that camera, and so that's how we're calculating the fields of view here. Then you can, another thing you can do is perhaps you want to contribute something back to the toolbox because you've added in a new camera. So you could actually add to this function camera list.m and add a new camera type and then contribute that back to the toolbox. Others could make use of that information. Here's some of the products that we end up generating. So in addition to the camera footprint, we output the long range and cross range resolution. And so I think that also comes out of your toolbox too. That doesn't one of your steps. Okay, never mind. And then we can plot it on Google Earth. And so this is actually an example of a station that we did on a river in Mississippi. And so you can see we were mounting it on a little pier that was on the river, and here was our resolution. A couple of limitations that we have in the toolbox right now. It assumes that if you have a multi-camera system that all of those cameras are the same. In fact, you might want to have different lenses on your cameras depending on what you're looking at in a multi-camera system. And so, for example, the FRF cameras that we've been looking at a lot today have different focal length lenses depending on which direction they're looking. At this time, we don't have that full capability to use different lenses in the toolbox or different camera types. Right now, it doesn't work with the local coordinate system is just relative to the camera, and then we have real world coordinate systems. We don't have the ability to rotate the coordinate system or translate the coordinate system. And so that's some functionality we would love to build in if somebody gets excited and wants to do that after the workshop. That would be a great place to start contributing to the repositories. And then finally, there's a little detail when you're doing this kind of a projection. You can actually end up projecting over where the horizon would be and wrap back around. And so this toolbox just takes care of that wrapping effect. And so here is a footprint that is approaching the horizon, but if we actually let it flip over the horizon, it would back project. And you get something funny and you would scratch your head and wonder what was going on. And that's because you were trying to project over the horizon. So we take care of that so you don't run into that problem. So in summary, you can find this toolbox on our GitHub repository. Also in it is a synthetic optical wave field code. And this is something that was developed by Eleonora Perugini, who's here today, based on some work that Chris Chickadell did during his PhD at Oregon State. And that allows us to produce synthetic images of a wave field. So that can also be really useful when you're designing a station, or perhaps wanting to do some synthetic analysis with one of the Pixel toolboxes. So the take-home points are here. Just if you're planning a new station, this is a tool that can help you. You can use it for both UAVs and fixed cameras. It can help you determine what kind of camera to use, and it lets you export things into Google Earth so you can have nice plots to share with your colleagues. And it's got a really low bar of entry, so you don't need to know a lot, even less than you know about or what you've done today in MATLAB. You can run the toolbox, so appropriate maybe for somebody who's got a CoSNAP station and wants to figure out what they might get from the CoSNAP station. And I think that's it. Anybody have questions on the station design toolbox? Okay. How about any questions in general for things we've covered today?
Going back to the run up and projecting at a certain elevation. Obviously the beaches are changing all the time, especially if you're looking over long term. I'm just thinking, instead of doing z=0 everywhere, the tides are changing, the water level, still water level changing, different wave conditions, etc. Instead of putting in, or maybe you could put in a changing, or actually change, the elevation of the transect or whatnot, or you could just put in a long-term average transect if you have available data. How much would that improve your predictions of the projection?
Yeah. Well, your errors could be, so if you sampled that z=0 and didn't correct for that, your errors could be on the order of, a couple of meters or more, if you're not accounting for that. So that's an interesting idea, taking an average of the beach profile rather than z=0. I think that could help get you in the right direction. And it also reminds me of something I wanted to say earlier, which is when you do have a long-term site, one important thing to do is going back and doing repeated surveys as that beach is changing. So, we always want to be, because we're missing that third piece of information that Kate alluded to earlier, when you're going from UV coordinates to XYZ, it's underdetermined, and the way to get around that is to actually have a survey of the beach, and having that regularly as the beach changes is really important in limiting errors, which can be pretty significant if you don't account for that. Good question. Any other questions?
Nailed it.
Yes.
How often would you say you need to resurvey?
Okay, so for the GCPs, for the extrinsic calibration, it really depends on the site. I mean, a lot of times in practice, I think people go years between resurveying a fixed site, and that can be okay if your cameras aren't moving, or it can be a real problem if not. One way around that is if you have a fixed, a long-term site, you could have long-term GCPs if you're lucky enough to have it in your camera in a place where you can put out GCPs that are just in the field of view all the time. And then you have a much better sense of if the camera is moving, or if you need to go back and recalibrate for a time when the camera moved and you didn't notice it.
You're cleaning the lens.
Yeah, right.
I think Rob is giving a presentation on auto-correcting those, and I think we've all tried different ways to do. But yeah, there's other. I mean, technically, if you could apply the SCP method, if you wanted to go through that, probably not the best one, but.
But in a lot of cases, just if your camera's not moving, you don't need to do it all that often.